Alright, hello everyone. Hello everyone. Am I live? Okay. I think I should be live here right now. Let me check. Let's see. Am I live? Alright, let's get started. So last time we talked about straight lines here, and we saw how we can plot them on a coordinate plane, and how we can solve a simultaneous equation, use three different kinds of form of the straight lines. And also we found more information about graphing straight lines and something more about perpendicular bisector. So what we're going to talk about today is sets and Venn diagrams. Today we'll probably focus more on sets. So let's get started. Alright, a set is a collection of distinct elements. What does this mean? Alright, let's say we have a list of elements. Let's say we have like 1, 2, let's say 3, 3, 3, 3, 5, or something like that. Let's say we had something like that. Then we should have we have 2 threes and everything else is distinct. So a set is a collection of distinct, so different elements. And what is an element? It's an object or a number inside a set. So since there is two same elements, and let's say if this was a list, then this would not be a set. This would not be a set. But if we had, for example, 1, 2, 3, 5, and we did not have a duplicate like we had up here, this would be a set. Alright, so that's what a set means. So a list, but without any repeated elements. And set doesn't have to be mathematic. It could be something like, let's say, red, well, green, blue. This could also be a set of colors. This is also a valid set. It's not mathematical, but it could be a set. So what if we wanted to know in mathematical notations if an element, for example, we have this set here. We wanted to know if yellow was in or is not in the set. If yellow was in a set, in this set, let's say we call this set color, all right? Is yellow in color? The obvious answer here is no. But how will we annotate this in mathematical terms? So if we have this symbol here, which shows that the element is in set A, where K and A is replaceable. So what does this mean? For here, if yellow, for example, green is in this set, right? Green is in color. So you write green is in with this symbol looking like an E, but it is not an E because this side is open here. And then, so because this side is open here, we can say that green is in color. And this would be how we annotate it. And that's why K is replaceable by the color green or the one of the elements. And then A is replaceable by the name of the set, which is color. So that's why we have the annotation green is in color. But what about yellow, which is not in color? We can write yellow is in, but is not in with a cross, is not in here, right here, is not in color, which shows that we know that yellow is not in the set of colors, as we can see here. Alright, so that's what we have. And then what is n of A? It's the number of elements in set A where A is replaceable. So it could be any set. Looking at this set of color again, the number of elements in color, we can count 1, 2, 3. So there are 3 colors in the set color. Let's take a different example looking at this. This is the set. This is a set, while this was not. So we will not look at this, but we will look at this. The number of, let's say this was a set called number. All right, the number of elements in here, let's count it, is 1 here, 2, 3, and there are 4 elements. So the number of elements in the set number is 4. And that's how we look at this. What is this symbol? An empty set, a set with no element. What does this mean? We have a set. We have nothing in it. So basically, there's just nothing. There is no numbers. There is no elements in it. So the number of elements in this, so we denote it as this. And generally we write sets in curly brackets, I think, is like this, which looks like this when you type it out. I don't know if you can see that. Yeah, it looks like something like that. But it does, I will not type it out. I will just write it. It looks something like this, and it does not have any element. Normal confusion comes from thinking that this contains 0, but it does not contain 0. It does not contain anything. This thing is empty, and therefore, if we use the annotation that we have done here, the number of elements in this set is 0. And there's only one set that does that, which is this set. And that's why we annotate with a 0 with a cross, or circle with a cross. And that's why it's also called the empty set. Empty set. Alright, so that's how far we got. So we have this empty set. What is finite and finite set and an infinite set? A finite set is a set where n of A, which is this expression we saw here, is the number of elements in set A, has a particular defined value. What does this mean? So we saw here, right? This is a defined value. There's a number. It's not defined. It's not like there is a lot of elements to the point that you cannot count. You can count it. There's 1, 2, 3 elements. Or in here, there's 1, 2, 3, 4 elements. So this is what we call a finite set. The number of a set, n of A, is defined. It is some number, let's say k, where k is defined and you can say what number it is. Even if it is like a quadrillion or like a million number or 10 to the power of like 1000, no matter what, no matter what it is, even if there is a number that can represent this, then this is finite. It can be counted and it is finite. So then what kind of sets are infinite? And we know that that means it has infinite amount of elements or is endless. Well, the simplest example would be the set of all natural numbers. So you go 1, 2, 3, 4, and then you go dot 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 until like as big as you want, even if it reaches this big number that you cannot even imagine, but it can still go on and on and on, plus 1, and then it will still go on. This is a set of natural numbers, right? This can be even bigger and bigger and bigger, right? So then this would be an infinite set because there wouldn't be an end to this. It is infinite. Usually an infinite set has this ellipsis or like which shows that there is like infinite amount of numbers. If it is shown by all of this, like how many elements there are, like it will be something like this, or they would be something like it will be n for n, which n where n is a natural number. I will not be bought where n is, I'm just gonna say n is natural, but understand that n is a natural number. These two are equivalent, so it is just saying that it's every single n where n is a natural number, and this is just listing all the elements. So this is an infinite set, an example of an infinite set. For two sets A and B. So now we're comparing two sets here. It's very important to look at two different sets and two different kind of stuff when we want to compare those two. So let's say we have a set A. Let's say it's just 1 and 2, just for the sake of simplicity. And then let's say B was something like 1 and let's say 3. All right, A is equal to B if the sets A and B have exactly the same elements. The sets are equal. Well, when one is exactly the same here, but 2 is not exactly the same as 3. So in this case, A and B is not equal. But let's say if we had another set called C and we had 1 and 2, it has exactly the same elements as A and no less and no more. So hence we can say that A is equal to C. All right, so that's what we can get from the first sentence. A is not equal to B if the sets A and B don't have exactly the same elements, which we showed here, and so we can say that A is not equal to B. All right, A is not equal to B because they don't have exactly the same elements, particularly because this number 2 is not in set B, nor is this 3 in set A. All right, let's just change this up a little bit, and let's say it's 1, 2, and 3. Then, and let's look at the next thing. A is is a subset of B. A is a subset of B if every element of set A can be found in set B. All right. So if every element in set A, 1 and 2, can be found in set B, 1 and 2 is both found in B, we can say that A is a subset of B. So even if we looked at C, which we wrote about it before, but let's take a look at it again. If it was 1 and 2 again, so then 1 is definitely in the set C and 2 is also in set C. So we can say that A is a subset of C. Alright, A is a subset of C. So what is this proper subset? A proper subset is the same as a subset, except that A cannot be B. So we would still say that A is a proper subset of B because of A not being equal to B. But since A is equal to C, we cannot say that A is not a proper subset of C. And note that we can also say that C is a proper subset of A. But C is not, C is a subset of A, but C is not a proper subset of A. Alright, that's what we have until here. So let's look at A and B using a previous example. Let's move on to a next tab. And let's say A was 1 and 2, and let's say B was 1 and 3 again. Just for the sake of simplicity, dealing with few elements is much more easier. All right, A and B, or the intersection of A and B, results in a set containing the elements that can be found in both set A and set B. The word "and" is very crucial here. Let me bold it. It's a really crucial word. So it needs to be found in both set A and set B. So let's look at the element. Let's say we look at the element 0. 0 is not found in A or B. So it doesn't satisfy the fact that it needs to be found in both A and B. It appears in neither. The number 1. So we can try and list all the elements of A, the intersection of A and B. Alright. Let's look at 1. 1 is found in A here. 1 is also found in B here. So we can say that 1 is an element of this intersection of A and B. Well, let's look at 2. 2 is in A, but it's not in B. So we cannot say that it is in both A and B. It's only in one of them. So 2 is not in this set. And so is 3, because 3 is not in A, but it is in B. So we cannot say it's in both. So therefore, the intersection of A and B in this case is just a set that only has 1 as an element. All right, let's look at the next. It's called union of A and B. It results in a set containing the elements that can be found in either A or set B or both. So it doesn't matter if it is in one or is in A or B or both. It just has to be present in one of them. So we can just list every single element that we can find. So 1 can be found. And note that we cannot repeat elements because the definition of set is a collection of distinct elements. So it must be different. It cannot be 1 and 1. So it has to be 1 only appearing once, and then 2 appearing once, and then 3 appearing once. And then we have this as a set of the union of A and B. Alright, so let's talk about the universal set. The universal set is denoted with a U and is basically what we are dealing with. Or it is basically the set that we are looking at. So if we were to say that U is 1, 2, 3, then we would be only dealing with these 3 elements. We would not be dealing with 4 because if we were, we would have put it into this. But since this is not in here, the main thing we will be focusing on is 1, 2, and 3. 4 is not an element that we will be considering in this case. And we can see this again, the set with all the elements that we are considering generally labeled U. Okay, so let's say we had a set A which had 1 and 2 as an element, and we're only considering 1, 2, and 3. Let's look at the next one. The complement of set A. It refers to all the elements that are in the universal set, but is not in A. So it is denoted with the set which is in the list that we are given, which is A, and then we denote it with a prime, which is what we call it. A prime is equal to the set of, if we are considering all the elements in the universal set, because it refers to all the elements that are in the universal set first. So it's 1, 2, and 3, which is not in set A. 1 is in set A, 2 is in set A, but 3 is not in set A, so 3 would be an element. And since there are no more elements that we're considering, there will be only 3. Note that if we did not have this definition for U, the definition for complement would be really hard to make or establish. Alright, let's look at some commonly defined sets. N is one of the most commonly defined sets. Is the sets of natural numbers. Is the numbers that we are used to growing with, like 1, 2, 3, 4, counting all the way up. It's just natural, and yeah, it's just 1 chair, 2 chair, 3 chairs, something like that. Or it's just the number that you can usually count. In IB, in this case, it will be defined as every number, every integer that is greater than 1, which is like greater than or equal to 1. So 1, 2, 3, and 4, and so on and so forth. But 0 is not included. And then we have Z, which refers to the set of integers. I'll just write int. Hopefully you guys understand what that means, integers. It involves negatives and 0 and 0 here. And then we have 1, 2, 3, 4, and so on. It goes forward, and it can also go backwards. The sets of all integers. And now if you are wondering how you would write natural numbers and 0 together, which is also a set that is very crucial, you can write either Z plus, which means that you are dealing with non-negative or positive integers, including 0. Or you can write it as N, and remember the union that we used earlier. Union, which means that the set of N and or including 0. So 0 and then all the natural numbers. Alright, let's go on. Q, okay, is the set of all rational numbers. What is rational numbers? Rational numbers are basically all numbers that can be written as a fraction. So for example, let's say we had 0 point, let's say 7. That could be written as a fraction as 7 over 10. So this would be a member of the rational numbers, or Q. It is not well drawn. It's something like is something like you're supposed to have a line here and it's really complicated to draw. But in the test or in some kind of places, you can just write Q and they will generally understand what you mean. And here you do not have to do the double stripe as well. You can just write Z and N and Z, but just ensure to get your point across. And if you don't think the examiner will understand, just write beside it, oh, the set of positive integers, or you can just write about it, the set of rational numbers, etc., etc. So we want to say that it's the set of rational numbers. But how do we define rational numbers? Because definition is really important in math here. We define natural number as all whole numbers, that is positive, all whole numbers that is positive or bigger than 0. We define integer as every whole number, positive integer, natural number with 0. But how would we define a rational numbers? All numbers that can be expressed in fraction, so in the form of p over q. But then if p and q had common factors, they can be cancelled out. So we would say where p and q is relatively prime, or you can say that they have no common factors except 1. And then we also need to ensure that q is not 0 in order for this to be a rational number. Alright, so that is the set of all rational numbers. So what about the sets that is not rational? We will just write as q prime. And generally, if we write q prime, we think of u as dealing with all real numbers, which includes q and so rational numbers and irrational numbers. So yeah, all u is basically that, which means that it's just all irrational numbers, which would include like root 2 or something like pi and something really bizarre like you can probably write some weird kind of stuff like root 3 or root 5. Basically any root that is not any square root that is not a square, any cube root that's not a cube. So let's say 7, and any kind of these kind of stuff will be the irrational numbers. And then for this kind of set with all rational numbers and the irrational numbers, it will be called all real numbers. Turns out the real number is not the biggest thing that you can get, but according to this point of the stage, you can just say that the real number is the biggest for now until we go on to the next level of IB for like AAHL or AIHL. But for both, for now, we would just look at the real numbers as the greatest set for now. So what is real numbers? Is all irrational numbers and rational numbers. But if we had a number line, we would say that it is just any number that can be plotted on the real number line. And that's why we have the set of all irrational numbers, the set of all real numbers, all numbers that can be placed on the number line. Alright, the next part is a bit complicated, so interval notation. Alright, let's go here. So let's say we wanted to define an interval that we want to specifically look at. Like for example, if we want to look at, for example, a variable x, where x is like greater than 0 but smaller than 1, and it would be useful sometimes if to define it this way. How would we write this so that mathematician would understand what you mean? Because if you just write for like this all the time, it might not be very efficient and you have to write it again and again. So you might be able to define a set, for example, S, where x is the element that we're looking at, right? And then this bar means such that x is greater than or equal to x and smaller than 1, for example. All right, so this would be what we have. And well, if we were dealing with real numbers, we would just leave this blank. But if we were dealing with, let's say, since between 0 and 1 there's no integers, let's say we were looking at all rational numbers, so Q, we would say that for all x, this is how we would read it, in the set S, for all x in the rational number, we are looking at all the x in the rational number such that x is greater than or equal to 0, but smaller than 1, and smaller than 1. Or for this example, when x is an integer between 0 and 10, for all x in the set of integers, or z, such that, so this bar means such that x is between 0 and 10. And as I mentioned, if we were assuming for all real numbers, and since that's the biggest set, if we don't write anything here, we would assume that we were talking about all real numbers. And then now we have this bracket notation, which is kind of annoying, but it's kind of fun to also look at it. So we were looking at all real numbers. Looking at intervals, we generally use closed brackets or open brackets. Something like open brackets like this. This is an open bracket, which sounds weird, and this is a closed bracket. Just remember that open bracket is like not like as tightly closed as like a closed bracket, but it's not really easy to remember. But this one is not including, and this one is including. So if we wrote 1 and then let's say 2, this would actually refer to the set of x in all real numbers, which we will not write, and then x is greater than 1, so not including 1, but is smaller than or equal to 2. Alright, that's how we would write it. We can also find some other ones, like we can just do 2 brackets, and then this would be exactly the same, except that it is just smaller and without the equals. We can also do 2 closed brackets, 2 open brackets, 2 closed brackets, or on the other side. And I think you'll get what I mean here. So you can write these out if you want, but I will be skipping through these because there's another really important concept to write about. And this is the concept of infinity. What if we have something like this? So what would this mean? Generally, if we did not have anything, and if this was actually a number, we would write something like this, right? But infinity is not a number. It's just a state of going extremely large. So even if x was like really, really large, infinity would even be larger, and to the point where you cannot count it. So you can literally just say that x can go up to as big as it wants. So you can just say that x is just greater than 1. And we can also do it with the negative side here. And note that we always use the closed brackets here, because it cannot be equal to negative infinity or infinity, because infinity is not a number. So for example, if we had something like this, then x is smaller than 1 for all real numbers. All real numbers that x is smaller than 1. So that's it for today. That's the bracket notation, all the sets that we covered, the universal set, the like functions or like the notations, and then we also looked at what sets an element mean, the elements, the number of elements, empty set, finite, infinite set, and yeah, and the complement. And today there wouldn't be any practice question because these are pretty basic concepts to talk about. And yeah, that's it for today. Thank you for listening, and see you soon, because soon I will have to go somewhere, so I'll be busy. So I hope you guys enjoy your rest of your day, and I hope you guys have fun.